So choosing a value is the most important part of the abortable consensus protocol. So in this slide we will start discussing how the values are actually chosen. And we will do this in an incremental fashion. We'll start from some fairly simple ideas, and then we'll see that they don't work, and then we will introduce incremental improvements or refinements to these ideas until we converge to the implementation which is correct. Okay. So in these slides we also introduce a few notions that we are going to use. So a leader proposes a value to processes. So proposes means that it broadcasts its value to a processes, and it will try to have a majority of processes to accept its proposal. Okay. So the chosen value would be required to be accepted by a majority of processes. So majority is also a quorum, according to our definitions. Okay. So this is what is required from a chosen value. So it must be accepted by a majority. And this is important because, as we said, we are guaranteed to have a correct majority in the system. And since any two majorities or any two quorums intersect, that means that even if process in the initial quorum that accepted a value fail, at least one process in this quorum will survive and will carry over this value to the rest of the system. Okay. So that motivates this notion of a chosen value as the value that was accepted by a majority of processes. So here is a simple algorithm for accepting the values. So that's accepting and choosing the values. That it is shown here on this diagram on the right hand side. And so basically it says that the process accepts the leader's proposal provided it has not accepted any prior proposals. Okay. And that actually works in simple scenarios like the one shown here. So in this scenario we have initially P1 as the leader, and P1 proposes its own value, so the value that was given to P1 through the propose event. And it just contacts three processes, P1, P2, and P3. So these three processes is a quorum, is a majority. And also this is the first value that any of these process ever receive. So in this case, every such process will accept that value. Okay. And since we have a majority, the value is actually chosen at this point. Okay. So now if later on another process, say P4, becomes the leader, it won't be able to get its own potentially contradictory value chosen because every two quorums intersect, and so any quorum that P4 will be able to contact, so for example P2, P3, and P4, will have an empty intersection with the quorum which had chosen the value of process P1 here. Okay, so this is the intersection. And any process in this intersection has already accepted a different value at the time P4 is trying to get that process to accept its own value here. Okay. And therefore it won't accept its value, it will reject that value, and for that reason P4 won't be able to get its own value chosen. And so we have just a single value that is chosen in the system, and this is what we want. Okay, so this algorithm is simple, and it's already moving in the right direction, but it is not, of course, fully correct. So it's oversimplifying a lot of things. So to understand where the difficulty is, we need to pay attention to the following constraint. So if the initial leader is correct and permanently trusted by everyone, so if we have a good leader right away in the system, then the algorithm must ensure that its proposal is chosen. Okay, so this is because this is the leader. Okay, so that's there won't be any other leader later on in the system, and this leader is going to propose and go away, right? So the system must ensure that this leader is successful. The algorithm must ensure that this is the case, and for that reason we have this constraint P1. Okay, so this is constraint P1 or condition P1, which must be satisfied by the algorithm, and it is as follows. A process must accept the first proposal it receives. Okay, and this is because, of course, if process has not received any proposals yet, it must treat the first proposal it sees as the proposal which is coming from the leader, which is going to be permanently correct. And it must enable this leader to choose the value, to impose its value. And for that reason, it must accept the first proposal it ever sees. Okay? And if we again look at this scenario that we considered previously, this is indeed what happens here. So we have P1 first as a leader, and then these three processes, P1, P2, and P3, receive P1's proposal, and this is indeed the first proposal that they have ever seen, and they're going to accept that proposal. Okay, and now we have a value chosen because there is a quorum accepting a value. Okay, so now notice that process P4 does not see the proposal of the leader P1, it sees the proposal of leader P4 first. Okay, and it will, of course, according to P1, will make P4 to accept its own proposal here. Okay, but this is okay because in this specific scenario, this is going to be the only process accepting a potentially contradicting proposal of P4, and this value can't be chosen because other processes in the intersecting quorum already chosen a different value, the value of P1. Okay, so in this particular case, requirement P1 does not cause any problem, so this is basically illustrates how requirement P1 or condition P1 is satisfied by the algorithm. Okay, so but now let's consider a little bit more complicated scenario. So in this scenario, the failure detector, or sorry, the leader, eventual leader component omega, trusts multiple leaders concurrently. Okay, and we know that that could happen initially, right? So initially, omega is allowed to make mistakes about the leader identity. And that could be a situation. And this situation, along with process failures, may cause a previously chosen value to be lost. And here's an illustration how that could happen. So here again we have a process P1, which is a leader, and then it proposes its value and makes sure that this value is actually chosen, so it's accepted at the quorum P1, P2, and P3. And then we also have a process P5, which is simultaneously considered as a leader because omega is making mistakes, say, let's say process P5. Okay. And so P5 goes ahead and proposes its own value, say blue value, which is different from the red value of process P1, and because we have to satisfy P1, the property P1, okay. So we need to accept, every process needs to accept the first value, the first proposal it receives. So provided it has not received any other proposals yet. Okay, so P4 and P5 may accept the proposal of P5. Okay. So, and the rest of the proposals are not, the rest of the copies of the respective proposals of processes P1 and P5 are not going to be accepted because they arrive late as shown here. Okay, so they're not going to be accepted. So now we have three processes in the system, which is a quorum which chose the red value, the value proposed by P1, and two processes in the system that accepted the blue value, so the value proposed by P5. So the blue value is not chosen, the red value is chosen. Okay, so we need to ensure that this value survives. But what could happen is that P3 may actually fail here. Okay, so you see the situation here. So P3 fails, so say disappears from the system, and now we have something like that. Okay, so we have two processes P1 and P2 accepted the red value, and another two processes P4 and P5 accepted a different blue value. Okay, and now if you want to learn which value was actually chosen, we can't do this because the value disappeared from a majority, from a quorum, because P3 is gone. Okay, so we don't have enough evidence looking at the system on the right to determine which value was actually chosen. So how can we solve this problem while maintaining the property P1 is shown in this slide. So we can actually allow processes to change their mind and accept more than one proposal, right? So here is an example how that can actually help. So if we have this situation that process P3 fails, and with it we have a symmetry between the value, the red value and the blue value, then if, for example, process P2 would have been allowed to change its mind, and after initially accepting the red value, later on switch to a blue value, then we have again a chosen value in the system. So in this case, it is this blue value. Okay, and so decision is reached. Okay, so it looks like it is necessary to enable processes to change their mind. So the first time they see any value, any proposal, according to P1 they have to accept it. So P1 still holds. But that's not enough. So in addition to that, they should also be able to change their mind in order to resolve the situations like the one shown on this slide. But if processes are allowed to change their mind, we have another complication. So now we can have potentially multiple chosen values. And the question is how we can disambiguate between different chosen values, right? How can we distinguish between these values. Okay, so how can we tell, for example, which value between the red one and the blue one has a precedence, which one is more important, which one was chosen and which one was not? Okay, so we need to invent a scheme in order to be able to do so. And the solution is going to be as follows. So we will identify each proposal with a unique ballot number. Okay, so recall that one invocation of abortable consensus is called a ballot. Okay, and so these ballots will have unique identities attached to them. Okay, so we refer to them as ballot number. So it is a separate question how these ballot numbers can be guaranteed to be unique, but that is possible to solve. So in particular, so one way is to identify each ballot through a pair, which is the process name and some sort of process ID and some sort of a counter. Okay. So if you look into the Paxos Made Simple paper, there is another proposal how we can have unique ballot numbers. But for now, for the remainder of this lecture, we will just assume that these unique ballot numbers can actually be generated and assigned to the ballots. Okay, so, but now we have another complication, and it is as follows. So how can we ensure, if multiple proposals can be chosen, that they all are consistent? And the key is that now we have unique identities to these proposals, which are the ballot numbers. So since they are unique, they induce a total order. And so we can kind of order these ballots in the increasing order, and then we can ensure this property P2 here, which says that if a proposal with value V is chosen, then every proposal chosen at a higher numbered ballot has value V. Okay, so these ballot numbers are going to be increasing, and then we start executing the system, and then at some ballot number, say ballot B1, okay, some value V gets chosen, and then by virtue of this property P2, we have that any subsequent ballot, B2, B3, B4, etc., will necessarily choose the same value V. Okay, so this is how we ensure consistency. Okay, so this property P2, along with the unique ballot numbers, unique ballot identifiers, gives us what we want. It gives us the agreement. Okay, and so of course this property P2 is nice and simple, but the problem is that it is actually not clear how we can guarantee this property in a distributed system. Okay, so we need to somehow translate this property or this condition into a code which can be executed by distributed collection of processes, right? And by the form this condition is stated, it looks entirely as an external property, as though someone is actually looking at our system from above and sees that this is what is happening, right? So for that reason, we need to actually continue refining a property P2. So property P2 is the correct one. This is what we need, but it is too high level. We need something which is more detailed, so it can actually be put into the code executed by each process. Okay, so we'll take it one step at a time. And first, what we will do, we will refine P2 into P2A here. And P2A is as follows. If a proposal with value V is chosen, then every proposal accepted by any process at a higher numbered ballot has the same value. Okay, so now notice that we are a kind of drilling down from this high-level view in which we actually see the quorums of processes. So a value is chosen if it is accepted by a quorum, to the process level view. So now we are talking about the values which are actually accepted by individual processes. Okay, so this value, this property P2A can actually suggest us a certain way of implementing the algorithm, of implementing P2. Okay, and it is clear that P2A actually implies P2. Okay, so as it is stated here. So make sure you understand why it is the case, but that's fairly straightforward. So property P2A is again moving in the right direction, but the problem is that it tells the processes what to do, but it does not quite tell the leader what to do. Okay? And that poses a problem if we consider property P2A in conjunction with property P1 that we introduced before. So property P1 must still be satisfied. And so here we see a problematic scenario. So again, we have a failure detector making a mistake, so we have two leaders, P1 and P5, simultaneously active in the system. And P1 succeeds to propose its value to a quorum, a red value V1. And here notice that we already have these ballot numbers here. Okay, so 1 is the ballot number used by P1. So now we have red value accepted by 3 processes, so they must do this due to the property P1. And so value V1 gets chosen at ballot number 1. Okay, so now we have a different process, P5, which also considers itself a leader, and it goes ahead and proposes a different value, a blue value, V2. And why it is doing that? Exactly because property P2A is not precise enough. It is not saying what the leader should do. It only says what the process should do. Okay, and so because of that, P5 can still propose a different value. And then this value arrives at P4. And because we still have P1, and this is the first value that P4 has ever seen, P4 must accept this value. So it will accept the blue value. Okay, and this blue value has a higher ballot number 2. And we end up in the situation that we violate P2A. Okay, and this is because we have to satisfy P1, and because P2A is not detailed enough to actually instruct a leader what to do, how to choose the value to propose. Okay, and this is the difficulty that we need to address next. So now we are going to refine P2A further into P2B, and P2B will actually instruct leader what to do. Okay, so it says the following. So if a proposal with value V is chosen, then any proposal issued by the leader of a higher numbered ballot has the same value. Okay, so notice that now we actually instructing the leader what it needs to do if it is the leader of a ballot which is higher than some ballot in which a value was chosen. Okay, so that leader must be consistent with that value. The proposal issued by that leader must be consistent with that value. Okay, and of course, since only the proposals issued by the leader can be ever accepted, P2B obviously implies P2A, and as we have discussed, P2A implies P2. Okay, and P2 is what we need for agreement. Okay, so so we have this property P2B, which actually says the leader what it needs to do, but of course, again, it is not detailed enough. So the leader must somehow learn if any value was actually chosen in one of the preceding ballots, or discover that no such value was chosen. Okay, and the instructions for that are given by this property or this condition P2C. So P2C is a further refinement of P2B, which gives the leader much more precise instructions as to what it should do in order to enable P2B, P2A, and P2. Okay, and this is what P2C says. So if a proposal with value V is issued, and of course that could only be done by the leader of a ballot B, then there is some quorum S of processes such that either A or B is satisfied. Okay, so property P2C says which values a leader of a specific ballot B is allowed to choose for proposing at that ballot. Okay, and so what are these conditions A and B? So A captures the situation that no value has been previously chosen. Okay, and this is as follows. So no process in this quorum S has accepted any proposal with ballot less than B. So in this case, so case A is that when no value was actually chosen. And we will see why it is the case in an example in the next slide. And B addresses the situation that some value was actually chosen at one of the preceding ballots. And so it says that in this case, V is the value of the proposal accepted at the highest numbered ballot among all the proposals accepted by the processes in S at ballots less than B. Okay, so property, so this subproperty B may look a bit unclear. Okay, so what exactly is going on here? Okay, so how it addresses the situation that leader must actually pick a value that was previously chosen by a quorum. Okay, so we will see this in the next slide. But now let's just notice that P2C actually can be shown to imply P2B. Okay, and we will see immediately why this is indeed the case. But for now, since P2C implies P2B and P2B implies P2A and P2A implies P2, so if we satisfied property P2C when choosing proposal as the leader, then we will have what we need. We have correctness, we have agreement. Okay, so now let's see the illustration of how property P2C works. Okay, so we have no process in a quorum S has accepted any proposal with ballot less than B, and B is the current ballot of a leader. Okay, so here's the illustration. So here we have a situation, say up to this point, that no value is actually chosen. So there were two attempts to propose a value with the ballot number 1 and ballot number 3. So ballot numbers don't have to be consecutive, by the way. They only need to be unique, right? So P5 was the leader and tried to propose V1 at ballot 1, and then P4 was the leader tried to propose V2 at ballot 3. So none of them has been chosen because they have not reached a majority. And so at this point in time here, we don't have a value chosen in the system. Okay, so why that could be the case? So for example, the remaining messages are delayed, right? So they're still somewhere traveling here. Okay, so in this case, a leader that sees, say, the quorum S, which is just P1, P2, and P3, will not have any proposal with the ballot less than its own ballot. So let's say we are talking here about ballot 5. Okay, so the next leader has ballot 5. So it happens to contact quorum S, and it does not see any prior proposal at either P1 or P2 or P3. So in this case, it can conclude that no prior proposal was chosen. Okay, so why it is indeed the case? It is because we see a quorum without any proposal chosen. So this is the quorum without any proposal chosen. And if any proposal was chosen, then then we will see some evidence of it at any quorum that we can see, at any composition of S which is possible. This is because any two quorums intersect. And since we have a whole quorum without any proposals, any proposals with the ballots less than 5 accepted, we can safely assume that no proposal has been previously chosen, and then we can go ahead and just propose, for example, our own value. Okay, so value V3 here, it might be different from both V1 and V2, and this is okay because no value has been chosen before this point here. Okay, so this is the illustration of condition A. Okay, so now let's see what happens in part B of property P2C. So here's an illustration of a possible scenario. So let's have a look in more detail what happens here. So in this scenario, we have 4 ballots from 1 to 5. 1, 2, 3, 4, 5. And ballot 1 is led by process P5. Ballot 2 is led by process P3. Ballot 3 P1, ballot 2 P4, and ballot 5 again P5. Okay. So now we actually have values chosen in this scenario, and the earliest ballot at which a value is chosen is ballot 2. Okay, so you see that P3 manages to get its proposal chosen as 3 processes, P2, P3, and P4, and it is chosen because this is a quorum, right? So let's denote this quorum as Q, and 2 is the lowest ballot at which a value is chosen, and the value which is chosen at ballot 2 is V2. So now what we want is that the values chosen on every subsequent ballots, or rather values issued at all the subsequent ballots, 3, 4, and 5, are all gonna be equal to V2. So let's see how part B of property P2C is going to imply this. So let's start going over the ballots in sequence. So let's start from ballot 3. The proposal value of ballot 3, which is V3, okay, is chosen to be the value accepted with the highest ballot by all processes in some quorum S. Okay, so any quorum intersects any other quorum, and so both S and Q are quorum. So S intersection Q is non-empty. That means that in S we are guaranteed to find either P1 or P2 or P3. So either one of these three is gonna be present in the set S. And we know that all of them actually accepted a value with ballot 2, which is value V2. And obviously, this is gonna be the highest ballot of any accepted value that we can see, right? Because the lower ballot can only be the ballot 1, and so 2 is higher than 1. So that means that this value V3 would necessarily be chosen to be equal to V2 according to part B. So now let's move to the next ballot B4, and let's see what proposal can be issued by the leader of ballot 4, which is P2. So again, by the same reasoning, we have some quorum S, and this quorum, of course, intersects quorum Q, and so again we are guaranteed to encounter at least one of P2, P3, or P4 in this quorum S. It means that the maximum ballot that we will see any value is accepted with is guaranteed to be at least a ballot 2 with which the value in this ballot was chosen. Okay, so the maximum ballot that we can see in ballot number 4 is greater or equal to. Okay, that means that the maximum ballot that we will encounter will be either 2 or 3. And as we have just shown, the value that can be accepted in ballot 3, V3, is equal to V2. Okay, and the value that accepted in ballot 2 is equal to V2. Okay, and that means that the only value V4 that we can pick and to propose at ballot 4 is either V3 or V2, and V3 is equal V2, and therefore V4 is equal V3 and equal V2. And so we can continue in the same fashion. So for B equals 5, for ballot 5 we get that V5 equals V4 to V2, and so on. And so from this reasoning we can conclude that P to C part B indeed implies what we need. So it actually implies P to B, which asks that once a value is chosen at some ballot, the values proposed in all subsequent ballots, x3, 4, and 5 here, will be equal to that value chosen. Okay, so we actually proved that P to C part B implies that. So now when we have this detailed condition P to C, our next task is to see how it can be translated into the actual code, into the actual algorithms executed by processes. Okay, so there are actually two parts to it, and the first part is as follows. So before proposing a value, the leader of a ballot B must learn the value accepted by a quorum at the highest ballot, which is less than B. Okay, and if you recall condition P to C, in order to learn this value, it is sufficient for the leader of ballot B simply to contact some quorum S. It can be arbitrary quorum. Okay, and then pick the value with the highest accepted ballot in this quorum. Okay, so this is the first part of the solution, and it is illustrated here. So for example, if you just look the process with ballot 4, so the leader of ballot 4, and before ballot 4 starts, we have these two values V1 with ballot 1 and V2 with ballot 3 accepted at different processes. And so the leader of ballot 4, instead of going ahead right away and proposing some value, it will first contact the system, contact some quorum in the system, and discover which of the previously accepted values has the highest ballot at the quorum. And so this is what the leader of ballot 4 is doing here. So it contacts a quorum, and the quorum here is P3, P4, and P5. So this quorum, the leader of ballot 5, of ballot 4, which is P5, manages to contact, and it sees two values. It sees value V1 with ballot 1 and value V2 with ballot 3, and the highest one is value V2 with ballot 3, so that is gonna be its proposal, okay, for ballot 4. Okay, so this is what the leader needs to do. So it needs to query a quorum in order to find out which value was accepted by a quorum at the highest ballot lower than its current ballot. But this is not enough. And why it is not enough? Because, as you can see again in this example, there could be another process, P1 in this case, which concurrently with P5 initiates another ballot, to ballot 5. Okay, and so And so this could happen because omega can make mistakes for some limited time, and both P1 and P5 may think that they are leaders at the same time. So if this happens, P1 will also query some quorum, and that quorum can be a different quorum from the one that P5 is contacting. And it may not see this value V2 at all, so it only sees value V1 with ballot 1 twice, and so it is going to be its proposal. Okay, and so we see that we can actually issue, in this case, two concurrent proposals for contradicting values. So this is not what we want to happen. Okay, so we actually need to ensure that these two proposals are consistent. Okay, and how that could be done? And the solution actually appears here in the second bullet. Okay, so we need to prevent all concurrent proposals with potentially lower ballot than ours to succeed. Okay, and by succeed I mean to be ever accepted at a quorum. Okay, so in this example, a proposal of ballot 5, so the leader of the proposal of ballot 5 needs to somehow prevent the leaders of all lower numbered proposals, such as P5, from succeeding at a quorum. Okay, so how that could be done? So to do this, the leader is not enough just do something at the leader. The actual processes need also to cooperate with the leader. And how they cooperate? They actually remember the highest ballot that they have ever seen, at which they have ever participated in a local variable, okay, in their state. Okay, and they would refuse to talk to any leader of any ballot which is lower than the highest ballot in which they ever participated. So in this case, so when we have these two concurrent ballots, ballot 4 and ballot 5, proceeding in parallel, what will happen? So the whatever process is being contacted first by ballot number 5, it will remember ballot 5 as the highest one in which they participate, and they will refuse to cooperate with any ballot which is lower. Okay, and so when that happens, so when P1 actually queries this quorum P1, P2, and P4, so all three processes in this quorum are locked. Okay, are locked for P5. For ballot 5. And that means that they will refuse to talk to any leader of a lower ballot. Okay, and so what happens is that when the leader of ballot 4 actually attempts to impose its proposal on the quorum, it will encounter at least one process that participated in proposal from ballot 5, and therefore it will never succeed. Okay, and that is of course provided that proposal of ballot 5 actually managed to get chosen, that it managed to succeed at the quorum. Okay, so if proposal with ballot 5 does not succeed at the quorum, then we don't care. So in this case, proposal of ballot 4 can go ahead. But if it did, then it will lock the quorum. so locked quorum. And by doing so, it will prevent any lower numbered proposal from any lower numbered ballot to ever succeed. Okay, so this is the second part of this mechanism that is needed to ensure the condition that condition P2C is satisfied. All right.